hello to everyone. So for this, for another session of the Lee Group seminar. So in this opportunity, we have the pleasure to have Corey Jones from Ohio State University, and he will speak about triangle presentations and tilting modules for SLN. So, and we agree with Corey that we can interrupt him for any question. So just turn on the microphone and ask, okay? So.
In case you can't turn on your microphone, just type in the chat and I'm going to read your question. So there's no problem with that either.
Awesome. Well, first I'd like to thank the organizers for inviting me to speak. And I should also mention about halfway through, we'll take a little 5-minute break and just to get some water or something like that. But yeah, so the purpose of my talk, I'm going to talk about these two things, triangle presentations and tilting modules for SLN. Triangle presentations are combinatorial objects that arise in the theory of affine buildings. So things like Brouillard-Titz buildings over non-Archimedean local fields, this sort of thing. While tilting modules are a full subcategory of the representation category of SLN over algebraically closed fields. And what the goal of this talk is today is to explain, a little bit about what these two things are. And then I'll show you how to build from a triangle presentation a fiber functor over the category of tilting modules for SLN. And these fiber functors have some exotic, I'll put that in quotation marks, exotic properties as fiber functors. And of course, the n and the characteristic of the field will depend on the triangle presentation yourself. Okay, so that's kind of the big picture overview about what we're going to try to do. But I'll start by just giving you a definition of tilting modules for SLN. My approach to tilting modules is quite pedestrian and elementary, and there is definitely a sophisticated point of view on these things. But for me, it's just a certain full subcategory of the representation category of SLN. So we have like K throughout this talk. K is just going to be some algebraically closed field. Then the category of tilting modules for SLN will be the full subcategory of SLN that you can construct as follows. First, we'll let V be the n-dimensional standard representation. And then we'll take the fundamental representations to be just wedge powers of V. And we'll take the full subcategory of rep SLN generated by tensor products of these wedge powers. And then we'll just take all the summands of those things. And those will be the objects in the category of tilting modules. And you just take all the morphisms between these representations. It's the full subcategory of rep SLN. And that's this category of tilting modules. Another way to say it is if you take these fundamental reps as these wedge powers of the standard rep, and you take the tensor category, full tensor subcategory of rep SLN generated by those, you could just take the idempotent completion. And that's the same thing as taking summands in some sense. Okay. And so why are people?
Can I ask a question?
Yes.
So this, are you assuming that the characteristic is bigger than n?
No, I'm not assuming that.
Because then it's not the same as the standard definition. So if characteristic is less than n, then exterior powers are actually not tilting modules in general.
Okay. Then perhaps we should assume that. Perhaps we should assume that the characteristic is bigger than n.
No, you should not. Pavel is not right. Tilting exterior powers are always tilting modules for SLM, not for other.
Okay.
For SLM.
Okay. Okay, I'm sorry. Okay, yes.
Okay, as I said, I don't know much about actual tilting modules. The category that I'm calling tilting modules, this is one I just defined for you. So I apologize if this isn't actually the category of tilting modules always. But yes, so this is the category. So wait, is it tilting modules?
Yeah. No,
yes,
sorry.
okay.
I did notice that V was basic representation. Sorry.
Okay. Yeah. Sorry. Okay. Very good. And so the reason that I'm interested in these things, so my background is really from the point of view of fusion categories. And if you take semi-simplifications of these categories by quotienting by the ideal of negligible morphisms, you get really interesting fusion categories in positive characteristic that are parallel to, these interesting in characteristic 0. If you take quantum groups at roots of unity and you take tilting modules and semi-simplify, you get categories with the same kind of fusion rules. So there are some interesting parallels here that make these fusion categories and positive characteristic quite interesting to me. But another point of view and another way that I come to the category of tilting modules is that there's a nice graphical presentation for these categories. And what I mean by that is if you study the characteristic zero representation theory, of course, the category of tilting modules is everything. That category is semi-simple. And so there's really nice, people have had graphical representations of intertwiners between representations since all the way back to, Feynman diagrams in quantum field theory. And there's a nice graphical description of this category, and you can notice that this presentations that you write down have a nice integral forms, and so you can just say what happens if I take this integral form of this graphically defined category and reduce it mod p, and it turns out that this actually describes this category of tilting modules. So from this point of view, you can view these tilting modules as idempotent completions of category, the integral form of the characteristic zero representation theory reduced to mod p. So these are kind of mod p reductions of the characteristic zero situation. So I'm going to start off by explaining what I mean by this graphical presentation. And to do so, I'm going to define an abstract category for you. Actually, I'm going to define two categories, web SLN plus or minus. Those plus or minus is a parameter that you pick. That'll just be a difference at the end of the description. Everything up till then will be basically the same. So I'm going to define a category with generators and relations. So I'm going to define, basically it's going to be a free, strict k-linear monoidal category. And the objects are going to be generated by just objects with labels in the set 1 through n. And if you're thinking of these as corresponding to representations, and we'll make that connection clear in a little bit, but right now, if you're just thinking what these objects should be corresponding to, 1 should correspond to the standard representation. 2 should correspond to the second wedge power, v wedge v, and so on and so forth. So the nth wedge power v is what corresponds to n. And then we're going to have morphisms. These are going to be the generating morphisms for the category. So if a, b, and a plus b all lie in the set 1 through n, then I'm going to have this trivalent vertex, which you interpret as a morphism from a tensor b to a plus b, and this other morphism from a plus b to a tensor b. And then I'm in addition going to have these two little lollipop morphisms that map from n to, in this graphical presentation, the empty space is representing the monoidal unit in this strict monoidal category. And then this other lollipop's mapping from the monoidal unit up to n. And what you do is you take the free, strict k-linear monoidal category generated by these objects and morphisms. So objects are just going to be sequences of elements from the set 1 through n, and of course there's also the empty label, which will be represented by empty space. And morphisms are just going to be all the pictures that I can make out of these little generators by sticking them together where the labels make sense and sticking them next to each other, taking their tensor product and composing along all the labels that make sense. And I'm going to take formal k-linear combinations of those pictures. So this is a free category, and it's much too free to be interesting or to be able to say anything about it. So then we're going to take that thing and quotient some relations. So this first set of relations I'll call the GLN relations because they don't involve the little lollipop, the map from n to the monoidal unit. So this first relation you can think of as a co-associativity type relation. The second relation is kind of an associativity thing. Here, I'll call this relation bygone bursting. And you interpret it as saying that this morphism in this free category should actually be equal to this scalar times the identity morphism, and that should have a little a plus b underneath it. This scalar, this is a combinatorial coefficient, a plus b choose a, and what I mean by that is take the integer in z and evaluate it in the field, so reduce it mod p, and that's what integer you put there. Here, these two relations are called the square switch relations. Okay. And so those are the GLN relations. I also want to impose some additional relations called the SLN relations. This first pair of relations, basically what it's doing is it's making the object n isomorphic to the monoidal unit, right? And if n is of course corresponding to the nth wedge power of the standard representation, then that should be isomorphic to the trivial representation. So we should have something like this going on. And then here's the difference. These next two relations, it's the difference between SLN plus or minus. So you pick one of these relations or the other one. You don't pick both at the same time. So the SLN plus relations tell you how the little lollipop morphism plays with the merging and split trivalent vertices. And so this is the SLN plus relation. Alternatively, you can pick the SLN minus relation, which has no sign there. One consequence that you can see of this is that this makes this monoidal category we've defined rigid, because the object A now has dual n minus A. But you can't use these trivalent vertices themselves as the duality solutions to the duality equation. I have to normalize one of them by a sign in order to get the cups and caps for duality. Whereas in the SLN minus relation, you can actually use the trivalent vertices with the lollipops assigned to be solutions to the duality equations. Okay, so there's two different categories here: web SLN plus, web SLN minus. It's the strict linear monoidal category that we just described, where plus or minus refers to whether I picked the plus relation, which kind of confusingly has that minus sign in it, or the minus relation, which does not have the minus sign in it. Notice if n is odd, then these two categories are just equal, because these relations, if n is odd, that n plus 1 becomes even, and so the sign goes away. So if n is odd, these are just actually the same relation. And so these two categories are just equal. Otherwise, they're genuinely different. You can think of this difference as like the relationship between the temporally Lie categories as defined by people who do planar algebras, right, with cups and caps and stuff going on. Those are like web SLN SL2 minus, whereas web SL2 plus is like the actual rep SL2. Okay, and I'll say more about that in a minute. And yeah, so along those lines, these are closely related to the Q equals plus or minus 1 quantum spiders of Caudice, Chemnitzer, and Morrison. So the comparison is a bit tricky, because those categories are defined as free pivotal categories, whereas ours are just monoidal categories. When Q is plus 1, it's not so hard to compare them, and you can actually find an equivalence between the underlying monoidal categories. When Q equals minus 1, it becomes a bit annoying, because in our categories, there's an obvious choice of pivotal structure using the cups and caps that we were given by the trivalent vertices. But unfortunately, it turns out that I think what's going on is that that pivotal structure doesn't agree with the pivotal structure on the Q equals minus 1 web categories. So I believe they're the same as monoidal categories, but the pivotal structure gets in the way. So it's kind of hard to unpack that and see it directly. But something like that should be true. Where our presentation with these generators and relation comes from is from the work of Brundin and Tova Eisenbud, Edinoff, and Ostrich, where they have these polynomial web categories. So basically the same categories we just defined, but only take the first GLN relations, and then we just add in extra relations that make the nth wedge power isomorphic to the identity and some compatibilities there. And that actually, that's how we're getting these. These are kind of quotient not in the sense of quotient by an ideal, but quotient in the sense of a monoidal category where you add morphisms to make things isomorphic that weren't isomorphic anymore. So that's what we did. We basically made the nth wedge power isomorphic to the trivial. And so it's kind of a quotient of this polynomial web category that they produce. And so that's the origin of these things. And so I apologize if this is really small. I just really wanted to fit it all in one slide. But how are these categories related to tilting modules? So it's actually the web SLN plus categories that have the relationship with representation theory. So there's a nice functor, a monoidal functor, which sends the generating object A to the vector space A wedge power V, as we said before. This map, the trivalent vertex, just gets assigned the exterior product, the wedge product map. So it should map from the A wedge power V tensor the B wedge power of V to the A plus B wedge power of V, and indeed you just take the exterior product. And then this map is this is just a fancy way of writing. If I had picked a basis or something when I was defining this, this is essentially just like a transpose. This is just a fancy way of getting the signs right, which I borrowed from the paper that I mentioned earlier. G is a representative of one of these cosets of minimal length, and you just take -1 to the length of it, and that's how you get the sign right and the permutation right. But basically, just think of it as a transpose of this kind of map, of this map here. And then under this functor, you assign the lollipops. You just pick some isomorphism from the nth wedge power of V to K, and the other lollipop gets assigned its inverse. you may notice that there's a multiplicative scalar's worth of choices here, right? There's not a unique isomorphism from here to here. There's just a scalar's worth. But it actually turns out that any choice you make will be monoidally natural isomorphic. So this monoidal functor is determined up to monoidal natural isomorphism modulo these choices here. Okay. So the theorem, which I'll attribute to Brundin and Tova Eisenbud, Eddinoff, and Ostrich from earlier this year, is that this above monoidal functor is actually fully faithful. So in particular, that implies it extends to an equivalence from the idempotent completion of this web SLN category to tilting modules, which can be viewed again as the idempotent completion of the full subcategory of rep SLN generated by these fundamental reps. Okay, and so this fully faithfulness is kind of the technical piece you need to get the equivalence from the idempotent completions. And if you look in their paper, you wouldn't find this result stated this way. In particular, they have their theorem is about GLN, but it's quite easy to take their result and boost it up to SLN. All the technical stuff is contained in their result, so I attribute this theorem to them. But one consequence of that is that if I have any other idempotent complete category C, and I have a linear monoidal functor from web SLN plus to C, that will extend to a linear monoidal functor from tilting modules to C, okay? Because by the universal property of idempotent completions. And in particular, we'll be interested when C is Beck, our favorite idempotent complete category. And the reason this is nice is because tilting modules, this category, is very complicated as a category. If I try to write down the indecomposable objects and the morphisms between them, and then try to find a functor out of that, it's not an easy thing to do directly. But this web SLN category is much easier, right? It has just a couple, just need to assign an object for each of the 1 through n. I just have to assign a map to each trivalent vertex, and I just have to check it satisfies the relations. So this point of view on tilting modules allows you to build functors out of tilting modules using this more easily using this presentation from WebSLN. And then this is just a side remark. If n is odd, of course, these are the same thing, but you might ask what happens for web SLN minus when n is even. And the claim is that you should have a similar theorem. I don't exactly know what to put inside this tilting module bracket. It should be some kind of u minus 1 of SLN integral form reduced mod p. I'm not exactly sure what it is, but there should be something there. And if anyone has any ideas, I would love to hear what you think should go there. And yeah, okay. Anyway, great. So one might be interested in studying fiber functors. So recall a fiber functor on a linear monoidal category. It's just a linear monoidal functor from C to Beck. So from a fiber functor, so there are many reasons people care about fiber functors, but just two of them that two reasons that I care about them. One is from a fiber functor, you can build new Hopf algebras using the Cohen construction. And, usually people care about fiber functors because not only can they build new Hopf algebras, but they can build Hopf algebras that reconstruct their original category as co-modules. That's this kind of Tanaka-Krein style reconstruction. Of course, in this level of generality, that's just not the case. You can build a new Hopf algebra, but you won't be able to recover your category C you started with as co-modules. At best, you can get a monoidal functor from C to the category of co-modules. But in general, it could have some kind of kernel, and it might not be essentially surjective. There's all kinds of things that could go wrong with that functor when you're just at this very general level. But anyway, you still get new Hopf algebras from this. So that's kind of a cool thing. You can produce new Hopf algebras and study them. They have some interesting properties. Another thing you can do with fiber functors is that if your category is braided, like in our case, these tilting module categories, they're braided, and in fact, they're symmetrically braided because they sit inside rep SLN. So there's just the swap braiding that switches the tensor factors. Well, if you have a non-braided fiber functor, then if you just look at the image of the braiding under this fiber functor, this produces for you new solutions to the Yang-Baxter equation. So that's kind of a cool thing. You can produce new solutions from these fiber functors, and you can get many of them just by picking your favorite objects in the underlying category. Okay, so these are some reasons you might care about fiber functors. And if you're thinking about fiber functors, this leads naturally to find all the fiber functors you possibly can. So tilt SLN, of course, has a standard fiber functor, which just forgets the action of SLN on all the vector spaces. And so each object is a vector space, and the morphisms are already linear maps. You don't have to do anything. The forgetful functor puts you inside vector spaces, and you're done. You have a fiber. But you can ask, are there other fiber functors? And in characteristic 0, the answer is yes. There are a lot more fiber functors. But in some sense, from some point of view, they're kind of boring. So I don't want to declare them all boring. They're not. They're interesting twists, and they're related to cohomology of the Lie group and all kinds of stuff. But they're boring in the sense that if I look at the dimension of a vector space assigned to some object, it necessarily agrees with the classical dimension. And by the classical dimension, I mean the object, the dimension of the object as a representation of SLN. So the kind of quantum dimension under the fiber functor has to be the classical dimension, the one that you started with. And this isn't too hard to prove in characteristic 0. But in characteristic P, you could possibly get much more interesting phenomena. In particular, the dimension, the quantum dimension, or the dimension of the vector space that your fiber functor assigns to an object only has to agree with the classical dimension in the field. So in particular, modulo P. And so this opens the door for possibly much more interesting exotic. I'll call it exotic. It's probably doesn't deserve to be called exotic because they seem to always be around. But they're more interesting than this characteristic 0 case. And indeed, as a proof of concept for SL2, it's quite easy to find these things because it turns out that the rep SL2, the tilting modules, at least the web category, web SL2+, is essentially the free symmetric or the free monoidal category generated by an anti-symmetrically self-dual object whose dimension is 2 in the field. And so you can just say, okay, what are vector spaces that satisfy that? And they're exactly vector spaces together with anti-symmetric, non-degenerate bilinear forms whose dimension is 2 evaluated in the field. Okay, great. So these things exist. They're not that interesting for SL2, but somehow that's not surprising. SL2, inside the whole SLN family, SL2 is almost, it's too easy in some sense because of this fact that it's essentially a free thing defined by, the free category generated by an anti-symmetrically self-dual object of dimension 2.
There is a question in the chat.
Yes.
I don't know if you want me to read it.
Yes, please.
Are we considering only fiber functors compatible with the pivotal structure?
Couple with, yeah. So that's a good point. I am not considering fiber functors coupled with the pivotal structure, but since we're in characteristic 0, since everything's semi-simple, there's essentially a unique dimension. The minimal dimension function is the classical dimension function, and I see what people are, when you say dimension, is there some pivotal structure going on? And the answer is no, but there is a notion of dimension you can use here that I'm just talking about dimension of vector spaces underlined here. But no, the functors, I'm not asking them to be pivotal or anything like that.
This is Victor Rostik. I asked this question.
Yes.
So, but where this condition about agreement of dimension modulo P comes from? I mean, why do we need it?
Just because the relation of so it always has to be sorry. So you mean in this number 4?
Yeah.
Yeah. Okay. So it's not actually clear to me that that is necessary. It's certainly these things certainly are sufficient. It's not clear to me in characteristic P if this agreement is necessary. In characteristic 0, it is necessary by having the unique minimal dimension function on this fusion ring because of semi-simplicity.
But why
I would have to
be minimal?
Well, if you have, so there's a theorem that says, and so this could be me betraying my my unitary background, where I think of everything in unitary and say what generalizes to the non-unitary thing. So maybe you calling me, I think this is still true in the non-unitary and not pivotal restrictions. But I think that the dimension of the vector space has to be less than or equal to what is it? What am I trying to say? Yeah. Okay. I think.
I think for SL2 you can send two-dimensional representation to space of any dimension greater than 2. I mean, greater or equal than 2.
But for quantum SL2 you can do that. But for classical SL2 you can still do that.
Classical. I think yes.
How does that work?
So in your point number 4, so what you need is vector space and bilinear form, but possibly non-symmetric at all. And there is some equation.
Well, but you have to assign. Remember, I'm talking about this web category. So the trivalent vertex, you know, or the cap has to get assigned to something. The cup has to get assigned to something, and when you compose them, it has to equal 2 in both.
Yes. But so what I'm saying is that this cup should be assigned to some bilinear form, but kind of non-trivial bilinear form, not symmetric, not anti-symmetric. Just
Victor, you need for this to have a solution of the equation. Q plus Q inverse equals to -3, for example, if you want to have a 3-dimensional space. And this equation is not satisfied if Q equals to 1 or -1.
But I think out of bilinear form, you build linear operator and you want trace of this operator to be maybe 2 or -2, something like this. And there are many bilinear forms. Anyway, so this is not really important for a talk, so let's
sorry. I would love to talk about this later. That's a good point, and it betrays my bias towards your thinking in unitary ways. So I apologize.
It's fine. So sorry for interrupting.
No. Yeah, but in particular, these things do give you examples. But perhaps they don't have to be the only examples. We should talk about that. Okay. Anyway, the question is, can we find examples in higher rank? It becomes much more difficult to find examples of fiber functors in higher rank because there's more morphisms and more equations that they have to satisfy. Instead of just asking for a bilinear form being non-degenerate and satisfying some stuff, you need much more. There's much more stuff going on that it has to satisfy. Okay. So right, and so here's where I was going to take a little break for a couple minutes. We can take a maybe I don't know how long, organizers. How long should we take a break for?
Maybe 5 minutes. We can
5 minutes,
take a tea or mate for the Argentinians here.
And but Victor, if you want, we can continue this discussion briefly. So you're saying that if you just take a non-degenerate form.
You want bilinear form, so bilinear form is the same as non-degenerate bilinear form. It's isomorphism from V to V dual.
Yeah.
And then you can take kind of transpose of it, so it gives you another isomorphism from V to V dual. So since it is not symmetric, it's going to be different isomorphism. And if you kind of combine them together, you'll get some linear operator from V to V, which can be written in terms of matrices. And my memory is that equation is that trace of this operator should be something like Q plus Q inverse, or maybe 2, or maybe -2.
Yeah, but so in characteristic 0, I like somehow 2 is like the minimal value that thing can take, the minimal absolute value.
Yes.
And the what am I trying to say? I think okay. You're saying any form whose trace the trace of what? The trace of you compose. Yeah, can you say that again?
Yeah. So you have essentially so you have this bilinear form, but it is not symmetric. So you have kind of form and you have its kind of transpose, and both of these forms they give you isomorphism from V to V dual. I mean, just by definition. And now you can kind of take one form divided by another, it would give you some map from V to itself, some linear operator from V to itself. So you have 2 isomorphisms from V to V dual, they differ by some linear operator. And equation is something like trace of this operator equals to plus or minus 2, something like this. And what I'm trying to say is that there are, in principle, you have a lot of freedom here, and this equation, I think it has many solutions, but I don't remember right now. But
yeah, so basically you're just saying you can just like rescale the duality maps by lambda and lambda inverse, right?
More than lambda. I mean, it's kind of lambda inverse, but it's kind of
in particular you could scale by lambda inverse.
Yeah. But you can kind of you can rescale. So essentially, one map which is cup, for example, is just standard duality, and cap is something that is kind of twisted by linear operator. So it's kind of something to which you add linear operator, which I think it should satisfy
it has to be compatible with the cup on both sides. Like you have to use the same map to be compatible with the cup on both sides. And that puts some restrictions on the properties of that bilinear form. But you're saying it still doesn't make it have to be like the transpose of the original.
What me think about this also.
Are all possible pivotal structures in this category is always integer in characteristic 0? The quantum dimension associated to the pivotal structure.
Oh.
Always an integer? Integer? I mean, can you change the pivotal structure in rep SL? I don't know.
Yeah, this is a good question in the sense that the same kind of story holds for quantum group, and for quantum group, quantum dimension is Q plus Q inverse, and usually it's not dimension of any vector space. So
yeah, but the point is that quantum dimension, like when you represent that quantum object on a actual vector space, so you use the fiber functor, the quantum dimension has to be bigger than the dimension of the underlying vector space.
Probably yes. That's probably
that's kind of the thing. And the point is, when you're less than 2, if I assigned vector spaces, it has to be smaller. But when you're 2, that's somehow the smallest. So I was thinking you can't have anything bigger than that. So you actually have to be 2. That was my intuition why I said that.
I mean, this might be related with some unitarity.
yeah. I mean, I know it's true for unitary, but you're right. That this might be simply a consequence of unitary. But aren't the pivotal structures?
If you take just usual quantum group and usual fiber functor and take Q to be on a unit circle, then Q plus Q inverse is something less than 2, but you still have standard fiber functor, and I mean, there is no problem with that.
Yeah, but that's not SL2.
Unless
that's
you care about category. Unitarity.
No, but that's not that doesn't give you a fiber functor of SL2. That gives you some weird quantum group category.
That's true. But what I'm saying is that Q plus Q inverse is now less than 2, and it's.
Yeah, but those categories are like not semi-simple and these sort of things. Or I mean, I guess
they might be semi-simple if you're on.
They might be semi-simple,
on unit circle, but not at the root of unity. It might be semi-simple.
Right. Yeah. Anyway, okay. Well, I can go ahead and continue with the talk. We should talk about this more later. I'll see if I can. Anyway, most of the fiber functors we know for actual rep SL2 look something like this, but maybe you can get a little bit more. Anyway, we want to go higher rank and we want to find new fiber functors and for the category tilting modules. So we're going to kind of shift gears to talk a bit about a source for these fiber functors, and it arises from the theory of affine buildings. So affine buildings, what are they? Well, from a bird's eye view, you can think of them as providing geometric structures for semi-simple groups that can be acted on nicely by semi-simple groups over non-Archimedean local fields. So think about things like a PGL and K, where K is the p-adics, or maybe the Laurent series over finite field or something like this. And roughly, you can think of these as geometric / combinatorial gadgets that are analogous to homogeneous spaces. And you get a lot of mileage out of studying Lie groups acting on homogeneous spaces. Think of these as analogs for these kind of non-Archimedean groups. And just a brief reminder, what is a Coxeter complex? Well, if you have a Coxeter system, it's a nice simplicial complex on which the corresponding Coxeter group acts nicely. We only care about the case of affine AN. And in this case, the Coxeter complex is simply, it's a tessellation of Rn via affine isometries by n simplices. So the easiest case to consider is when n equals 2. And then the simplicial complex we're talking about is just take, the standard tessellation of the plane by equilateral triangles, right? Everyone's favorite that you do in grade school with the shapes, and you draw in all the shapes, and you take in equilateral triangles and you fill up the plane. Think of that as a simplicial complex, and that's the affine A2 Coxeter complex. And affine ANs are essentially generalizations of that idea. Okay, so a building of type affine AN is going to be a simplicial complex that in some sense is modeled on these affine AN Coxeter complexes. So it's going to be a simplicial complex which is a union of subcomplexes called apartments. And each apartment is itself a Coxeter complex of type affine AN. And it has to satisfy the following conditions. So if I pick two simplices, any two simplices, there's some apartment or affine AN Coxeter complex that contains both of them. So this means that this isn't like a disjoint union of Coxeter complexes. These Coxeter complexes are appearing in there at all kinds of angles in every direction you can think of. Anytime I pick two simplices, no matter where they are in this complex, there's some Coxeter complex containing both of them. And if I have two simplices which are both contained in apartments A and A prime, there should be an isomorphism of Coxeter complexes from A to A prime that fixes S and T pointwise. Okay, and by fix it pointwise, I mean it really fixes the vertices. It doesn't just map the simplex S back to itself. It really fixes the vertices of the simplex. Okay, and that's it. That's a building of affine type AN. And so here's an example. I won't go into too many details about this in the interest of time, but these are the so-called Bruhat-Titz buildings for the group PGLN-K, where here K is a field with discrete valuation. You can build an algebraically, you can build a affine AN-1 building where you basically take the vertices of this thing are lattices over the discrete valuation ring inside K to the N. I won't go into details, but you can look at this slide later if you want more details. But that's this is kind of why affine A and Coxeter buildings are really important, because they're the buildings which this group PGLN-K acts nicely. These are the kind of structures that it acts nicely. Okay. I'll give you a more combinatorial characterization in a minute, and the way that we're going to do that, just recall a definition. If a group's acting on a set, the action is called simply transitive if the map from the group to the set given by G to GX is a bijection for any X. And of course, it's sufficient to just say it's a bijection for a single X. And this has a bunch of other definitions. This might be called regular action. It might be called free and transitive. There's a lot of different words. This simply transitive is a little bit old, but it's kind of used in the context of these groups acting on buildings, which is why I picked the terminology. And what's the significance of this? Well, if a group is acting on a building delta, and it happens to be simply transitive on the vertices, then you can actually recover the entire building just by looking at the Cayley graph of gamma with respect to a special presentation called the triangle presentation. So how do you build one of these things? Well, pick a vertex in the building, okay? Since the group acts simply transitively on the set of vertices, then for each of the nearest neighbors of that vertex, there's a unique group element that maps V to that nearest neighbor. So take those group elements that map that vertex to its nearest neighbors, and because their building has to be connected and all kinds of stuff, that set of group elements has to generate the entire group, okay? And so now what you want to do is find a presentation in terms of those generators that are going to capture each of the simplices. And these things are built up out of triangles. So you end up, it suffices to write down the triangles that you can build out of these generators. And so you end up with something called a triangle presentation. And you can write down axiomatization of what kind of abstract presentation will be coming from one of these groups acting simply transitively on an affine AN building. And I'll say that theorem in a little bit, but first I'm going to tell you the combinatorial definition of a triangle presentation. Okay, and to do that, I just want to remind you guys about finite projective geometries. And the reason is that if you have a locally finite building of type affine AN-1, then if you take any vertex, you can look at the collection of vertices neighboring that initial vertex, and consider, an incidence relation between them if they're adjacent, right? If there's an edge between them in the building, and it turns out that you can prove that from those axioms we wrote down earlier, that set of neighboring vertices with that incidence relation will form a finite projective geometry. So there's an abstract definition of a finite projective geometry in terms of incidence relation, but I'm going to give you kind of a concrete almost universal example in higher rank, at least, of a concrete finite projective geometry. So let V be a finite vector space of dimension n over a finite field FQ. Set pi j to be the j-dimensional subspaces of V, and let pi just be the union of j goes from 1 to n minus 1 of pi j. So pi is just the set of all proper subspaces of this finite vector space. And then you can define an incidence relation on this set. A is an incident with B if either A is contained in B or B is contained in A. And this set pi, together with that incidence relation, is an example of a finite projective geometry whose geometric dimension, whose geometric dimension is n minus 1, which is, that n minus 1 matches with that n minus 1 and is 1 less than this n. So it's the geometric dimension n minus 1, and the order of the geometry is Q, and that Q is the order of the field that the vector space goes over. And as I mentioned earlier, really what we use in triangle presentations is an abstract characterization of projective geometries as incidence geometries, but it turns out that in geometric dimension greater than or equal to 3, all abstract finite projective geometries are isomorphic to ones of the form I just described. So for geometric dimension greater than or equal to 3, basically what these things are all finite projective geometries. These incidence relations are everything. But in dimension 2, there are exotic examples, and these are projective planes is a whole area of research understanding all these exotic nonlinear examples, and those are included in what I'm going to say in the future. So I mean abstract, but I just told you concrete for the sake of those who are not familiar with this sort of thing. Okay, so here we are, triangle presentations. What are they? A triangle presentation of type affine A n minus 1 and order Q consists of a finite projective geometry pi of geometric dimension n minus 1 in order Q. And we also have an involution. So it's a map from pi to pi that squares to the identity, and it maps this set pi I to pi n minus I. So it kind of flips the dimension of the objects, of the subspaces. And then the meat of this is a subset of pi cross pi cross pi. So it's a collection, I worded this kind of funnily. It should be a collection of triples, or in other words, a subset of pi cross pi cross pi, satisfying the following combinatorial conditions. So this tells you when are u and v in there for some w? Well, they're in there exactly when sigma of u and v are distinct and incident. So incident in this projective geometry. This relation just says that this set T is invariant under cyclic permutations. This third condition says if I look at the dimension, because remember, think of these as subspaces of a finite vector space. This says that the sum of the dimensions of all these things is 0 mod n. Okay, so that in particular, because of the restrictions on dimensions of subspaces, it's either n or 2n, one of those two things. This says if u and v are in there, there's at most one such w for every u and v. That can be the third element of that triple. So it's kind of if u and v, if there's u, v, and w1 and u, v, and w2, well, w1 and w2 have to be the same. And then this says that if I reverse the ordering of everything and apply sigma, that also has to be in T. So T is closed under this operation of reversing the order implying sigma. And then the last one seems quite strange. I'm not even going to read it out loud. You can just look at what I wrote there. On the surface, it seems quite strange, but when you go to build the fiber functor, you say, this is just the associativity and co-associativity of our SLN thing. So it actually ends up being interpreted as something quite natural in this interpretation under fiber functors, but it looks weird as written. And okay, so this is the definition of a triangle presentation. And why do we care about these? Well, given one of these things, I can define a discrete group where the generators of the group are just the elements of pi. So they're the proper subspaces of a vector space. And then I impose these relations. So G sigma u and GU should be inverses of each other. And then I apply the relation GU, GV, GW is 1 for every triple UVW in T. Okay, and so I really use T to build a presentation for a discrete group. And the theorem, due to Donald Cartwright, is that if you have a triangle presentation, then the Cayley graph of this group I just described with respect to this presentation is the one skeleton of an affine AN-1 building. And indeed, you can just take the flag complex over the graph. So in other words, just define the n simplices in my complex to be the subsets of size n, so that every or n size n plus 1, so that every pair of vertices is adjacent in the graph. So you just take the flag complex of the Cayley graph, you get an affine an-1 building. Conversely, if I take any group which acts simply transitively on the vertices of an affine an building and satisfies this technical condition called type rotating, then if you do that construction we said earlier to make a presentation, then that exactly will be a triangle presentation. So in some sense, these combinatorial objects, which we just defined as finite, as a collection of triples of a projective plane satisfying some combinatorial conditions, that actually characterizes groups acting simply transitively on the vertices of affine an buildings. Okay, so in some sense, this combinatorics that we wrote down here is capturing the essence of very symmetric affine an buildings. Okay, that's the philosophy. That's what these things are. So here's an example. So this is an example for affine A2. And so in general, this will give you an abstract projective plane. But so let Q be some prime power and let N be Q squared plus Q plus 1. Then we're going to take a subset of Z mod NZ that has Q plus 1 elements. And this subset will be called a difference set. And that's why we have this letter D. And it should satisfy the following two properties. Every element in Z, every non-zero element in Z mod NZ should be able to be uniquely written as a difference of two elements in D. Okay. Second, I want to make sure that multiplying by P, where P is this prime here related to this Q, I want to make sure that multiplying D by P leaves D invariant. So here's an example for Q equals 4 equals 2 squared. And D is just this set with 5 elements. You can check it satisfies all those properties. Okay, so from this is called what's called a cyclic planar difference set, and it's studied by people who do combinatorics and this kind of thing, like really old school style combinatorics. But you can define an abstract projective plane from this in an involution as follows. So set pi1 to just be the group, the Z mod NZ itself. Pi2 to be the collection of sets, which are just translates of D. So just take D and take all of its translates by group elements, and that collection of those sets will be pi2. And then we'll define an incidence relation. So if M is in pi1 and S is in pi2, well, they're going to be incident exactly if this element is in that corresponding set, right? So it's just containment, and that's it. And then you can define a nice involution. So I want to define a map from pi1 to pi2. So I need to take an element of Z mod NZ and produce a translate of D. What do? Well, I just take D and translate by the element. Okay, so it's the obvious thing. And of course, the map going backward, you can check that's a bijection. So the map from pi2 to pi1 will just be the inverse of that. And then, and then you can define T prime to be this collection of triples inside pi1 cross pi1 cross pi1, defined by this formula. T double prime is just take T prime, reverse the order, and apply sigma. That lands us inside pi2 cross pi2 cross pi2. And so that's T prime prime. And I'll just take the union of those two things. And that, it turns out, is a triangle presentation. Okay, so that's one way to construct one from this combinatorial structure of a cyclic planar difference. Okay, and then of course, now you have the recipe to go build an affine A2 building combinatorially. You can just take this, use the recipe for building the discrete group, take the Cayley graph, and there you go. There you have an affine A2 building. Okay, great. So what we're going to do is we're going to take a triangle presentation of type affine an-1, and we're going to try to build a fiber functor on this web category, web SLN-. Okay, so we're going to pick some algebraically closed field. There's going to be restrictions on all of these things later to make this work, but right now let's just try it. We're going to take like a K be an algebraically closed field. We're going to take a triangle presentation of type affine an-1 in order Q. And now we need to take for each object A. So going back to the web categories, remember I need for each of those objects 1 through n, I need to assign a vector space. Well, VA is just going to be the formal linear combinations of the elements pi A, where these are the A-dimensional subspaces in the projective geometry. And then just because of some conventions, we said pi n wasn't anything, so we're just going to set Vn to be K. You could have set up a convention where pi n was was a singleton. It was the whole, the whole space thought of as a subspace. But we didn't do that, so I'm just going to assign Vn scalars. And this is just some notation. If I have something in pi A, and pi B, and pi A plus B, I'm just going to write down these matrix units, E, U, comma, V to W. This is going to be the matrix unit, right, which takes the basis element U cross V of VA tensor VB and sends it to W, which is a basis element for VA plus B. So it's just the matrix units and 0 on everything else. So this is just some notation, writing down these matrix units. And then we will do this. So I'm going to assign the trivalent vertex. It's supposed to map from VA tensor VB to VA plus B. Well, I'm just going to sum over all those matrix units that go from VA tensor VB to VA plus B, where this triple U, V, sigma W is actually in the triangle presentation. And what this TAB means, it's just some notation, which I should have explained. It just means it's the stuff in the triangle presentation T whose first entry is in pi A and the second entry is in pi B. So it's just saying that it goes from A tensor B to something. So that's what this thing goes to. This one from, remember N got assigned the scalars. So I just assigned this matrix unit and U, sigma U to 1, the unit in K. And similarly, I just do for these maps, I just use the transpose matrix unit there, go here. The lollipops just get assigned, both things are K, so I just use the identity map. And then this takes us to the theorem. So if K has characteristic P greater than 0, and P is greater than or equal to N minus 1, and Q, which was the order of the triangle presentation, is 1 mod P, then the linear maps that we just defined satisfy the relations of Web SLN minus. And in particular, if N is odd, then by that stuff we explained earlier about the universal properties of idempotent completion, this assignment defines a fiber functor on tilt SLN. Okay. In general, you're getting on this Web SLN minus category, but when N is odd, they're the same, and so then you can apply that whole stuff to get a fiber functor on tilt SLN. All right, and I should mention that these are exotic, again, in quotation marks, and as Victor was pointing out, perhaps not as exotic as I was trying to claim that they were, but in particular, the dimension of the standard rep, for example, is quantum N, where I use the combinatorial convention for quantum N, right? Q to the N minus 1 plus Qn minus 2, blah, 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 which is much bigger than N, as long as Q gets large. And for every N and P, as long as P is greater than or equal to N minus 1, you can find infinitely many triangle presentations and infinitely many Qs for infinitely many Qs. And so you can make this as large as you want. So you can make these things as big as you want to. And so these kind of give you these interesting fiber functors. So some questions about these things. What can you say if you apply the Cohen construction? You can get some Hopf algebras out of these. What can you say about those Hopf algebras? You also get some solutions to the Yang-Baxter equation, which when you write them down actually look pretty nice. In the paper there, I do say a little bit about those in some cases and what they look like, and they look pretty nice in combinatorial. What can you say about them? Of course, they're involutive solutions to the Yang-Baxter equation because the braiding on SLN is symmetric, but there's still these interesting, ones in characteristic, positive characteristic. What can you say? And then a big question that I have, which is kind of every attempt I've tried to make sense of this has failed. Is there a geometric explanation for these fiber functors? Like there's all kinds of relations between representation theory and buildings that come from, like things like the Satake correspondence, which don't fit. This picture that we're talking about here doesn't really fit in that picture at all. But is there some kind of analog there? And my attempts at doing this haven't worked, but of course I don't understand the geometric side well enough to have any kind of confidence about whether there is something there or not. But I will say that this condition that Q is 1 mod P is quite mysterious from this geometric point of view, and I don't quite understand what's going on there. And then finally, I should mention about where I actually came from these things. I think I mentioned earlier on, I secretly come from this, world of unitary categories. And Stefan Voss and Matthias Balvikins were studying, so they basically took these maps I just defined for you in the Affine A2 case, and they said, consider these maps defined from a triangle presentation in Affine A2, take the rigid C-star tensor category generated by them inside Hilbert spaces. This is some nice semi-simple rigid C-star tensor category, and it defines a compact quantum group under Tanaka-Klein duality in that case. And they were studying these because these actually are the first examples of Katz type, at least their discrete duals are the first examples of Katz type quantum groups with property T, and so they give you property T von Neumann algebras, and so they're very interesting, and you use this categorical version of property T to prove this. And so I was looking at these things, and I noticed that when you reduced their thing mod P, you ended up with SL3 relations. So the same story goes here. You could just define these maps in characteristic 0, and they generate some kind of tensor category, and somehow when you reduce them mod 3, they're giving you fiber functors for tilting modules of SLN. So the question is, can you clarify the relationship? In particular, can you use the fact that the mod P reductions give you fiber functors for SLN to understand the original characteristic 0 categories, or vice versa? Can you use the characteristic 0 categories to really understand these fiber functors? And that's it. I'm going to go ahead and stop there. So thank you guys for your time.
So thank you very much, Corey, for the talk. So are there any questions or comments?
Yes, I have a question. Can I ask a question?
Yes, absolutely.
Of course.
So about this n=3 comment that you made at the end. So does that imply that you have exotic fiber functors for SL3, quantum SL3?
No, exactly. Yeah. So exactly. So no. But that was the point. I believe that's what Stefan and Matthias were looking for, was exotic fiber functors for SL3. But instead, they didn't find them. They found these other ones that didn't work. So no one found those. And so instead, they found these things coming from quantum groups. But when you look at from their definitions, there's a natural presentation for the category that looks kind of like SL3. And so my original hope was like, oh, maybe these things are exotic fiber functors for SL3. So I tried to make them satisfy the quantum SL3 relations every way I could. And it didn't work, but they did satisfy modulo P. Right. So the categories they define in characteristic 0 are genuine quantum group categories, but they're not quantum SL3. There's something different that bears some kind of resemblance to SL3, but the resemblance can be best characterized, I believe, is that when you reduce them mod P, they are giving you SL3 fiber functors. But I tried really hard to get a quantum SL3 fiber functor from these categories that they define, but no, it doesn't work. So these relations that you define don't even satisfy quantum SLN relations. They just like, there's a whole extra term there that you never see in these quantum SLN spiders that just doesn't appear. They're just incompatible. But if you reduce it mod P, that extra term goes away and you do get SL3 relations. But that's an excellent question. Yeah.
So the question is, okay, so what they did is not a solution, but maybe you can just do linear analysis in the neighborhood of your solution in the p-adic direction to try to lift them to characteristic 0, and then you will get some linear equations.
Yes, yeah, that's exactly what I was hoping for. Yeah, something like that. But my knowledge isn't robust enough to do p-adic analysis.
No. There is no. It is a very elementary thing. You just write, perturbation, and you compute the tangent space basically.
Right.
So maybe there is you can deform it in the direction of characteristic 0. This is just writing down the equation. So try to construct a solution over Z mod P squared. And so you're actually all of your everything is in FP, or you need
no. So it's over an algebraically closed field characteristic. It's in P, but which P you use, like if you fix a triangle presentation, then you can only pick P. So P is allowed to vary, but if you fix one triangle presentation and has order Q, you can pick any P that divides Q minus 1, basically. And so there's going to be finitely many.
But the category will be over algebraically closed field of characteristic P, but perhaps you only need some finite extension.
Yeah. I mean, in fact, the fiber functors themselves are defined over. Yeah, they'll just work over any field of characteristic P. So.
Over FP in particular.
Yeah. It will work over FP. That's right.
Right. So then try to lift that over mod P squared.
Okay.
Yeah, you can try to lift them.
No, tengo que dejar porque estoy en una reunión.
What? Yeah. So what I was trying to say is, can you lift them over Z mod P squared? So try to construct a solution of your equations over mod P squared, which mod P gives you a solution. So then you will get some equation for the for the so you have already some number mod P, and you lifted mod P squared, so you have something like A plus P times B, and you will get some equations for this B, and which will be linear, and then you will try to solve them.
I see. I guess you could ask, will this work in the very easy case of SL2, where we kind of like understand everything better? With that sort of, like if you picked a, if you were using, like from the very early on, we said, okay, you can build fiber functors from vector spaces with anti-symmetric, non-degenerate linear forms.
Yes, it will work, because in that case, you can describe the scheme of solutions, which is just this, given by the equation trace of E times E transpose to the -1 equals to -2. So it's just a scheme of variety defined over Z, and so in particular it has a deformation in the p-adic direction.
Okay, very interesting. Yeah. Excellent.
Any more questions?
So what I have another question. What would that be a solution to exactly? So like, would that define? Would you hope to find that to define a fiber functor for quantum SLN, or like what would that be a solution to?
Well, maybe for quantum, but maybe even for classical. Like Victor explained, there is doesn't seem to be an abstraction to existence of such a thing. For example, for n equals 2, there are functors from the usual rep SL2 to vector spaces, which are exotic, of any dimension, actually greater than 2.
Yeah.
And so possibly, and also for quantum. But among quantum ones, there might also be unitary ones, which is the thing you are most interested in, as far as I understand.
Yeah, that's right. That's correct. Yeah.
Classical one will not be, it won't be possible to be unitary.
That's right.
But when you lift it to characteristic 0, you will get a functor of a p-adic field, which when you cannot talk about unitarity, but it will be defined over algebraic number field, and then it can be embedded into the complex field, and that you can talk about whether it's unitary or not.
I see. So I see. Okay. So this can give you exotic characteristic 0 fiber functors on higher dimensional spaces in particular. Like the standard thing can go to something higher. I see. Okay. Very cool.
So are there any more questions or comments?
This is Victor Ostrик. So am I right that your formulas for this fiber functor, they kind of say that these triple vertices, they go to monomial matrices? Is this?
Yes, that's correct. Yeah.
So I mean, it sounds kind of very natural to ask to classify all solutions like this. I mean.
Yes, I totally agree. I actually meant to write that as one of the bullet points, is does this classify all such solutions?
I see.
Yeah, that's a very good question. And I think the answer is yes. But there's something funny going on.
Mm-hmm.
In particular, I assumed P is greater than or equal to n-1. But I think this should actually be true for all.
For any P?
For any P. I don't think you really need that assumption. It's just harder to verify the relations, because the relations when P is greater than n-1 reduce to something a bit easier. That's easier to check.
So this condition is kind of
this
trouble
condition.
with the proof.
Yeah, exactly. And so when I try to classify all relations, I run into this problem square on. So I mean, I'm trying in particular to see, you know, if this restriction is fundamental. The problem is it's really hard to work with actual examples that don't satisfy this condition, because once the examples get very large, concrete examples of triangle presentations are hard to come by. In fact, I don't think there's anything that's concretely written down as a combinatorial set for n bigger than or equal to 4, and that makes finding primes that don't satisfy this condition very, very tricky. But yeah, so in answering your original question, does this classify all of them? You run into this question about, does this P greater than or equal to n-1 even need to be there for the sufficient? Like, is that even sufficient to do? But yeah, no, that's a very good question. And in fact, doing that for not just these categories, but for other categories, you might call those fiber functors like combinatorial fiber functors, because you know, because then these morphisms just define subsets of some set, right? And you can ask for combinatorial conditions that characterize them. So you might imagine a big program of classifying all these for lots of representation categories, spiders like this. But yeah, no, that's very interesting. Yeah, good question. I don't know the answer.
Yes, that sounds interesting to me.
So does it mean that you're getting set theoretical solutions of the quantum Young-Baxter equation, or they are not set theoretical?
No, they're not set theoretical. Unfortunately, they're not, because even if you do it over finite field, you still have to tensor over the field. So yeah, no, these solutions are not set theoretical. The matrices they're not permutation matrices on the bases.
But they are sparse matrices.
They're sparse. They're definitely sparse. Yeah. There's only a couple non-zero entries, and the entries are very combinatorial. Like, you can characterize which entries have it just in terms of things in the triangle presentation. So I in the paper, there's a little bit about that. I'd say a couple words about that, not too much.
Right. So this is a good news for the approach that I suggested, because if you have a very simple kind of solution, then linear equations characterizing the tangent space will be much simpler. And so maybe you can see if you can solve them and if there are abstractions and so on.
I see. Very interesting. Yeah, that sounds like a very interesting direction to go. Yeah. As I mentioned before, I'm not an expert in any of this. I think those of you who know me know that. I just kind of stumbled into all this stuff on accident, and so I'm trying to learn everything as I go. So, but that sounds excellent.
Okay, more comments, questions?
Yeah. Is it too naive to think on extending this to the orthogonal group or to the symplectic group?
So I think the answer is no. That would be a very cool thing to do. And then you might look for, instead of using affine AN buildings, you might use affine BN or CN, whatever. Like, you try to do this for all the types. There's two major problems for trying to do that. One, you're not going to be able to use this formalism of groups acting simply transitively on the vertices, because those Coxeter complexes are not symmetric enough for there to possibly even admit a group acting simply transitively on the vertices. It'll have to be something more complicated. So it would be nice to figure out what kind of action on a building will produce the right combinatorial structure to get a fiber functor for these other types. I believe something will work, but I don't know exactly what the answer is. That's thing one. Thing two is that there's not a nice spider-like description. There are planar algebraic descriptions of things like orthogonal group and symplectic group, and there are descriptions of those, but I don't think it's in the same web style. Like, it's not in the right basis, quote unquote. That's analogous to this web basis of that we were talking about here. So it may work. Like, you try to do something like the BMW algebra or something as a description and try to do something there. That may work, but I think you'll need some general description of those orthogonal symplectic categories in a web thing, and I don't think that's been. I think recently there was some work that just like in the last month or something that did this for rank 2 maybe, or maybe even rank 3. I forget. It was some, actually I think Cooperberg already did the rank 2 case. The rank 3 case I think was maybe even rank 4. I don't know. There's some incremental advances, but there's not like a general family where you can expect a general thing here. So. Yeah. Oh, yeah. And also the equivalence with tilting modules is another thing. Like this was all done in characteristic 0 quantum land. You still have to match it up with tilting modules, which becomes more difficult when you don't have, things like skew-Howe duality and that sort of stuff. So anyway, I expect it to work, but there are some obstacles that obvious obstacles.
Yeah. So one more question about this Weiss and Val-Wickens business. So you say that they constructed some category, some semi-simple category, which is close to quantum SL3, but not quite quantum SL3, right?
Well, I was hoping that it was close to quantum SL3, and when I tried to make it, I realized the actual analogy was SL3 was a mod P reduction. So it only is close to quantum SL3 in the sense that it has, the same kind of generator. But when you write down the relations, there's like this extra term that you want to go away but doesn't go away. And so it's close in some kind of abstract sense, but maybe not in a quantitative sense. But yes, I'll say yes here.
But is it known what the Grothendieck ring is for that category?
No, not completely. No, it's not completely known. It's only like some fusion of some small even just writing down all the simple objects is not known. In fact, there are some very basic questions about the category that we don't even know the answer to, like, does the category only depend on Q, or does it actually depend on the triangle presentation that you pick, right? Because you can have different triangle presentations of the same order, but the little pieces of the category that they were able to work out, which were sufficient to get their property T result that they were after, it didn't depend on Q. So they have this open question: does it even depend on Q or not, the underlying category? But yeah, no, there's little known about these categories. They're pretty, and that's why I was studying them, right, to try to understand more about them. And I kind of ended up doing this mod P thing on accident. I guess you could say, yeah.
But how come, this category? So when you work in characteristic 0, this is some kind of big category that you don't understand. But then when you reduce it mod P, the relations mod P, in principle, when you reduce relations moduli and ideal, the quotient, the ideal can become smaller only, and the quotient becomes larger somehow. So how come you get something simple mod P while?
Well, I didn't say you get something simple mod P. You just, the relations that are satisfied by SL whatever, but there could be some kernel there, right? Like, I'm not saying that this category is SL3. It just takes a fiber functor from SL3, right? And so in some sense, it's a question about planar algebras or something like that. So the characteristic 0, you're going to have some maps that have you're going to have generators 1 through n, and you're going to have some maps, and they're going to satisfy some relations. We don't know what the relations are that these things satisfy that uniquely define the category. But those relations do have an integral form. We know that because of how you defined it as monomial matrices. So if you reduce the planar algebra mod P, then that category takes a fiber functor from this SLN web category. Okay, but we're not saying that somehow this category is simpler. On the contrary, it may become more. It could be just as complicated. Just like how tilting modules in characteristic P are more complicated than regular representations in characteristic 0. It's that kind of analogy. Right, it's like taking tilting modules in characteristic P instead of taking all modules in characteristic 0 or something. So that's the way to think of it.
But is it known, for example, if you take a tensor power of V in this category of these two people and take endomorphism algebra in characteristic 0, is it known what this algebra looks like?
No. Just in the two-dimensional. If you just take 2 tensor powers, I think they were able to work out enough about this algebra to get what they want. But I think, no, not in general, for general N. I mean, they have these kind of partitions. I mean, there is a combinatorial description, right? Because you can just use these maps. It's generated by these maps. But somehow you don't have relations. You just do a state sum model over the triangle presentation. And so that's really not a satisfactory answer, right? You can say, okay, here's a spanning set given by pictures I can draw out of these trivalent vertices, and then I can define a relation which basically does a state sum model. But no one has been able to extract out from that generators and relations, that, you see what I mean? Like, there's a state sum definition, which is not very useful for describing the algebra as an abstract algebra. That's my point.
But how is it related to the algebra in characteristic P? Now, algebra in characteristic P, the same kind of algebra, we understand more or less because it is endomorphism algebra in the tilting category. So
no. It's a quotient of the endomorphism algebra in the tilting category. There could be some non-trivial ideals, and identifying the ideal, I don't know how to do that. I mean, tilting modules will have a lot of non-trivial ideals, right? Because they'll all be contained in this negligible ideal, but there's lots of weird ideals inside there. And identifying that, I don't really know how to do that. But maybe you're right. I mean, so I agree. This, if you take that thing over Z, if you take the endomorphism algebra, instead of defining it over C, if you define it over Z, and you reduce mod P, you will get a quotient of the tilting module endomorphism stuff. That I agree with that. But first of all, it's a quotient, and there's some non-trivial ideal, and I don't know how to identify that ideal. But maybe that is a good approach for trying to understand the characteristic zero algebras, and that's exactly the kind of thing I was hoping for. Would be to understand those characteristic zero ones by these mod P reductions in terms of tilting modules. Yes. So that that.
But you say that the fusion rules were computed for small examples, and do they coincide with SL3, or they actually
No, they're actually different. So if I take the quote unquote fundamental representation and I tensor it together, all the old ones appear, but there's an extra one that you don't see in SL3. And what happens when you reduce mod P is that kind of term goes away in the fusion rule.
Oh.
In some sense. Yeah. So no, it's not SL3 fusion rules. We know it's not, even just from doing the small examples. There's like extra stuff there that when you reduce mod P disappears.
So this is like you take this tilting category maybe, and you do quotient by this ideal, and then you. I mean, how is it related to semi-simplification maybe?
I don't know. So I know that whatever ideal I write down is contained in the negligible ideal. So if I quotient by this thing, and then I semi-simplify this category, I should get the same thing as if I just semi-simplified the original tilting module category. So in some sense, you can think of this, if you semi-simplify these categories in characteristic P that you get from quotienting by the ideal, this is a perfectly good category. If you semi-simplify, you will get the semi-simplification of the original tilting category because the ideal has to be contained in the negligible ideal. But I can't say more about it than that. I can't actually identify the ideal at all. I don't know how to do that. It seems like it's quite difficult, actually. Somehow we're missing something, some concept. I'm missing some concept, but it's similar to the same kind of questions that Stefan Voss and Matthias Valbekins were struggling with when they were trying to ask this question about really just finding a nice planar algebra generator relations description of this category in characteristic zero. There's some interesting difficulties there. It's related to the problem that we can't classify, at least for n equals 2, it's not unrelated to the fact that we don't even have a classification of projective planes, right, upon which these structures live. The difficulty in classifying the projective planes is similar to the difficulty of like identifying the relations here. That's just me saying my own qualitative thing. I don't know how to make that concrete, but in doing the proof, I kind of was running into the same sort of issues, which was interesting to me. Yeah.
So we know what the semi-simplification of tilting modules in our paper, it was computed, but
yes. That's right.
Maybe using that you can.
Yeah, the problem, yeah, right. That would be excellent. because the semi-simplification of these guys are the semi-simplification of tilting modules, right? So using that knowledge, maybe you could say something about the characteristic zero case. Yeah, that would be excellent.
Well, I mean, you can maybe estimate fusion coefficients or something like that.
Yeah, probably you could do something like that. I agree. That seems plausible.
So you can compute the dimensions of endomorphism algebras in terms of fusion coefficients, but in the dimensions of endomorphism algebra in characteristic zero category are greater than or equal the dimensions in the semi-simplified category.
Yep. That's
and
right.
so this gives you a bunch of inequalities for fusion coefficients.
Oh, yeah, that's right. Yeah, absolutely.
And maybe it makes sense to write them down and see what they mean.
That's right. That's very interesting. Excellent. I think that does make sense to do.
More questions? Comments? Okay, so we thank Corey Jones again.
Thank you.
Thank you, Victor and Pavel, for coming also.
Oh,
You are welcome.
It was my pleasure. Thanks. I learned about this from Pavel. So.